Alright, you know it, I know it, we all know it. It's time for another of Matt Parker's Maths Solutions. I'm Matt Parker, and the math solution this time is for the takeaway triangles puzzle, which was the 9th of Matt Parker's maths puzzles. There you go. Thank you very much, everyone who's been joining in, sending in answers. This time, we had a very good success rate. So we had 1,807 submissions. So that's people who went on the form and put in their solution for the submittable part of the puzzle. And of that, get ready, we had 1,756 correct answers. That is 97.2%. So a very impressive correct answer submittable thing rate. So well done, everybody. As always, if somehow you're new to this, what you're seeing next to me there is what's on my computer here, because we go through and we load up some of the things that people emailed in. So as well as the, just over 1,800 people who submitted an answer, we also had the usual torrent of emails. We've gone through and picked out some of our favorite ones. So David here cracked one of the possible ways to generate, infinitely many correct answers. No wonder so many people got it right. So you can pick your number and you add 7 to it, and then use the number where you add 7 twice. So that will work out quite nicely. Oh, and they've correctly ruled out x being 0. David, I like how thorough you are. So there you are. That's one way of looking at it. A slightly more general way of doing it, which includes the one that David had. Rob here showed that you can have 3 starting numbers. And, oh my goodness, where A, B, and C are, they don't have to, do they have to all be different? I don't think so, but they probably can't be all the, there you are. So, there's a nice generalization there. So you got your target number, which was deliberately an even number. You divide that by 2. And then you have, you can have B can equal C. That works for me. Sorry, that hadn't occurred to me. The whole time I was putting this presentation together and going through it all, I never stopped to think, hang on a second, we can make them, B and C can be the same. So there you are. The way I thought about it was, I just thought you need to have 3 numbers, which the difference between them is a multiple of 7. That's how I went about it, which is, what this is saying for the case where you want to get 14. So thank you people who generalized it and showed it. We had a bunch of people coding it up. So Alexandria here did it in Code Studio, and they put this together, they said, quite quickly. So it doesn't do anything fancy. You've just got to look at the actual debug console to see the output as it happens, which is quite nice. We also had a Scratch submission. So Deanna, who puts together this presentation for me, she's a big fan of Scratch, and so Gregor, good work. There you are, we put your Scratch submission in. And of course, we got a whole bunch of Python. Our favorite Python one this time was from Peter here. I'll put a link to it on GitHub below. In fact, I'll link to the Scratch and Studio Code ones as well, of course. And this one, Peter used it to find 3 numbers. Peter's 3 numbers were 1, 92, and 99, because they took the maximum amount of time before they settled into just 3 things that cycle over and over and always give you a sum of 14. Fun fact, the numbers I came up with when I was solving this originally, I picked 5, 12, and 103 because it takes 14 iterations before the sum becomes 14, which I thought was very pleasing. I didn't realize that's the maximum value you can have with numbers below 100. I picked 103. I got lazy. I had 5 and 12, and then I moved the next number up until I hit something that took exactly 14 iterations, and I went over 103. Turns out I could have gone 1, 92, and 99 to have the same thing more efficiently. Good job, Peter. So Tobias wrote up a whole paper about this, and oh my goodness, they broke it down. They looked at how it links to the Fibonacci numbers, all the rage at the moment. So I will link to Tobias's paper below if you want to check that out. It is very comprehensive. And Willem. So second last thing I want to show you here. Willem, actually, I'm just going to play. This is from their website. I'll link to it below if you want to go check it out. It does these cool animations because Willem wanted to look at what happens on different polygons. So don't just do triangles. What if you do squares and pentagons and, hexagons and, whatever else you want to do, heptagons or septagons, depending on how you fancy it, all the way up. And they also noticed that the number of states it goes through when it finally starts to cycle, if you search for those numbers, of course, they come up on the online encyclopedia of integer sequences, although not under what we're looking for. So it's not like this is the generalized takeaway triangle. It's under the maximum cycle length in differentiation digraph for n-bit binary sequences. There you go. Although if you look down in the notes there, the length of longest cycle for vectors of length n under the Ducci map. Ducci was an Italian person, a mathematician, I guess, who in the late 1800s was the first person to look at takeaway triangles. And this process of where you take a list of numbers, which the vector that they're referring to here, and then you substitute it with the differences, the absolute value of the difference between all the sequential pairs, including the last one, with the first one, that process of taking one vector of numbers and turning it into another one by doing exactly what we did on the triangle, but for whatever length you have, that's called a Ducci map or transformation. And so you can have whatever length n, we were doing 3, you can look at how long it takes for a cycle, or more specifically, the maximum cycle length. So some people, it depends on numbers you put in. You can put in numbers, put in all zeros, and it will stay all zeros, right? So this is the maximum length you can have. And actually, if we zoom in there, so because we're no longer attached to polygons now, you can have a case for n equals 1 and n equals 2, but they'll be static, not very exciting at all, incredibly boring. They're trivial. Triangle, there's your first non-trivial one. It's got a cycle of 3. Squares, no cycles. And then pentagons, a cycle of 15 possible. You're able to get a cycle of 15. And then what have we got next? Hexagon, cycle of 6. Heptagon, cycle of 7 up to. And then octagons, those cycles again, static. And that is what Willem was showing with this animation. So as you can see, the triangle is cycling through 3. The square, nothing. And the octagon, nothing. And then the other ones you can see they're going through. And the pentagon is just going mad. Look at it go. So it's a great visualization for that way to generalize it. And actually, I haven't put this in the presentation, there are some open questions about what happens with Ducci mappings between vectors. And so I came across a paper. I forget who it's by. I will link to that below. It's got a bunch of open questions about these things. And obviously, we did it with integers. You can get far more excited and put all sorts of other crazy things in there. As the last thing I'd like to show you, Ronald did. Ronald used complex numbers. And so, started with a triangle with I, -1, 1. Ronald. I mean, I hate to choose a favorite, but this time, you're my favorite. And then showed, of course, you get spirals. So, I mean, what's not to like with that? Absolutely incredible. So thank you so much, everyone who got involved with solving this puzzle. As always, thanks to Deanna and Oliver for giving me a hand to put all of this together. And in theory, we'll be back next week with another puzzle. So thank you so much, everyone who plays along and enjoys these puzzles. We're going to, what are we up to now? 9th? So we'll definitely do a couple more, but if people keep enjoying them, then I guess we'll try and keep on making them. I hope, it's nice we've got a community of people solving them, and we'll keep going. So thanks for getting involved.